In this problem, we have data in a tabular form. It is also a no calculator problem, so let's see the information that we're given. Train A runs back and forth on an east-west section of railroad track. Train A's velocity, measured in meters per minute, is given by a differentiable function VA of t, where t is measured in minutes. Selected values for VA of t are given in the table above. Part A, find the average acceleration of the train A over the closed interval from t equal 2 to 8. The average acceleration is going to be the average rate of change of velocity. So that is going to be the slope of the secant line. So essentially in part A, what they're asking us to find, we'll call it A average, is the slope of the secant line from t equal 2 to t equal 8. So I'm going to focus on those 2 points and write this down so that we have VA of 8 minus VA of 2 over 8 minus 2. So we have negative 120 minus 100 over 6. So we have negative 220 over 6. And velocity is in meters per minute, time is in minutes, so this is meters per minute, or if you prefer, meters per minute squared. Let's take a moment and take a look at the scoring for this. So the scoring for this is simply 1 point for calculating the average acceleration. Don't forget units. It doesn't specify that. They probably wouldn't take off points for that, but you should do that anyway because sometimes they do specify that and they will take off points for that. Part B, it says, do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time between t equal 5 and t equal 8. Give a reason for your answer. So at t equal 5, the velocity is 40. At t equal 8, the velocity is negative 120. So negative 100 is between those two values, and we do know that VA is a differentiable function. So what does that mean? Well, since VA is differentiable, it is also continuous. Therefore, by IVT, since VA of 5 is equal to 40 and VA of 8 is equal to negative 120, VA of t is equal to negative 100 for some t greater than 5 and less than 8. You have to invoke the intermediate value theorem there. You have to justify using it because the velocity function is differentiable and therefore continuous. So let's see how they scored that. VA is differentiable, which implies it is continuous. VA of 8 is negative 120, VA of 5 is 40, and negative 100 is between them. So therefore, by the intermediate value theorem, there is a time t between 5 and 8 such that VA of t is equal to negative 100. So you have to justify by showing that negative 100 is between the two velocities at time 5 and time 8, and you have to make that conclusion using the intermediate value theorem. Alright, let's take a look at part C. At time t equal 2, train A's position is 300 meters east of the origin station. 300 meters east. So that would be in a positive direction. Because remember, right is positive, left is negative, up is positive, down is negative. So east is to the right. And the train is moving to the east. Write an expression involving an integral that gives the position of train A in meters from the origin station at time t equal 12. So this is relevant, this is relevant. Use a trapezoidal sum with 3 subintervals indicated by the table to approximate the position of the train at time t equal 12. So let's start out with the integral expression, and then we'll work on finding the trapezoidal sum. So this problem really goes back to the fundamental theorem of calculus. So if we integrate from time 2 to time t, and I'm picking time 2 because we know the position at time 2, the velocity function va of t dt, we will get the position of A at time t minus the position of A at time 2. But we know the position of A at time 2, it is 300, or positive 300. So if we want to find the position at time t, we are going to have to solve for xa of t, so that's the integral from 2 to t of va of t dt plus 300. The problem asks us to find the position at time 12, so xa of 12 is the integral from 2 to 12 of va of t dt plus 300. And now we're going to have to find the Riemann sum using the trapezoid rule for the integral portion of that. Alright, so here's the work necessary to evaluate that integral expression using the trapezoid rule. I encourage you to pause the video and look at the table and compare what you see on the screen in front of you to the table and think through the process of using the trapezoid rule to find that integral of va of t from 2 to 12. And then don't forget, when you get a final answer, technically this does not need to be simplified, but you do want to put units on it. So let's take a look at the scoring for that problem. You get 1 point for the position expression, which is this right here. You get 1 point for the trapezoidal sum, and that is part of that integral expression, and then you get 1 point for the position at time t equal 12. I think we've covered that sufficiently because this whole expression right here covers the integral expression portion, and then when you add the 300 to it, you get the position at time 12. And for the last part of this question, it is a related rates question, which is something that a lot of students struggle with. So pay attention to this, and if you have questions about it, make sure you ask. A second train, train B, travels north from origin station. At time t, the velocity of train B is given by vb of t is equal to negative 5t squared plus 60t plus 25. At time t equal 2, the train is 400 meters north of the station. Find the rate in meters per minute at which the distance between train A and train B is changing at time t equal 2. So I think that you need to have a good visual of what's going on here. And really what's happening is you've got train A heading east, and you've got train B heading north, and we're trying to find the distance between them, and we'll call that C. So let's call this A, and we'll call this B, and we'll call that hypotenuse, the distance between them, C. So we know that A squared plus B squared is equal to C squared. What we're trying to find is the rate at which the distance between them is changing. Find the rate in meters per minute at which the distance between train A and B is changing at time t equal 2. So we know that A, B, and C are changing with respect to time. So what we're going to do is we're going to differentiate this equation with respect to time. So we have 2a dA dt plus 2b dB dt is equal to 2c dc dt. And we are solving for dc dt, which would be equal to the following. It would be equal to 2a dA dt plus 2b dB dt divided by 2c. You can factor out the 2's, so those will cancel out. And now basically what you have is you have xa at time 2, va at time 2, because that's the derivative of the distance for train A, plus xb at time 2 times vb at time 2 divided by xc at time 2. And you can verify these various values for xa, va, xb, vb, and xc. And so when you get done with that, you're going to have basically 300 times 100 plus 400 times 125 over 500. I think a simple way to simplify this is to divide everything by 100, so these zeros can cancel out, and you end up with 300 plus 500 over 5, or 800 over 5, and that would be in meters per minute. So let's check the scoring on that. 2 points alone for the implicit differentiation. That's a big one. Okay, so basically getting to here is worth 2 points, and then you get 1 point for the answer.